Hello, my dear students. Welcome to the ninth lecture on particle physics. In the eighth lecture, we stopped at discussing the idea of isotopic spin. And let me start from there. What I had tried to convince you that isotopic spin was assigned to those particles which participate in a strong interaction. That means we are talking about the hadrons. And why it was done? Because for the first time, it was found that if we switch off electromagnetic interaction, then there is no way to distinguish between a proton and a neutron. Similarly, there is no way to distinguish among pi plus, pi zero, and pi minus. And the algebra of for the isotopic spin was developed with the same analogy as that of the angular momentum. When we talk about the projection of the isotopic spin, the convention is the highest charge state is given the maximum projection. That means, let me just give you an example that proton and neutron, they are member of the doublet, where I is half for both of them, but the projection I3 is plus half for the proton and I3 is minus half for the neutron. If I talk about pi plus, pi 0 and pi minus, then the highest charge state is given the maximum projection. This is a triplet, therefore I is 1 for the triplet and I3 will be plus 1 for pi plus, I3 will be 0 for pi 0 and I3 will be minus 1 for pi minus. Therefore, the doublets are assigned isotopic spin half, triplets are assigned isotopic spin 1, quartet like deltas, those exist in 4 charge states, they are assigned isotopic spin 3 by 2 such that the projection of isospin I3 is plus 3 by 2 for delta plus plus and then minus 3 by 2 for delta minus. Now, if I talk about the antiparticle of these four, then as you know that antiparticle of delta minus is delta minus bar, and delta minus bar means the charge is now plus 1, while delta plus plus bar means the charge is minus 2. Therefore, if we write them, then this will be delta minus minus bar, then delta 0 bar, delta plus bar, and delta plus plus bar. Now, isotopic spin for them will be 3 by 2, and then projection will be plus 3 by 2 for minus delta minus bar, plus half for delta 0 bar, minus half for delta plus bar, and minus 3 by 2 for delta plus plus bar. Therefore, the important point is always we take care of this fact that the highest charge state should get the maximum projection. Similarly, if you take the example of K plus K0, which are placed in a doublet as they have got the same strangeness quantum number plus 1, we put K plus at the top and K0 at the bottom because the charge of K plus is positive while K0 is negative. They have got strangeness quantum number plus 1. Similarly, put K0 bar and K minus this time, like K0 bar at the top and K minus at the bottom. And then why we are putting them together? They have got strangeness quantum number to be minus 1. Similarly, we can have sigma plus, sigma 0 and sigma minus. These are the three sigmas where when you switch off the electromagnetic interaction, their masses are exactly the same. Okay. Therefore, the important point is for quartet, we assign isotopic spin 3 by 2. For triplet, we assign isotopic spin 1. For doublet, we assign isotopic spin half, and for singlet, we assign isotopic spin 0. What are the examples of singlet? Like we have discussed in one of the classes, it is lambda 0, omega minus. If you consider baryons, similarly you have lambda 0 bar, you have omega minus bar. Or if you take the example of mesons, then mesons, you have eta 0, you have eta 0 prime, you have omega 0, you have phi 0, and many, many more. Therefore, there are many singlet baryons, there are many singlet mesons, and all those singlets are assigned isotopic spin quantum number 0. And if I is 0, that for sure, that means the projection of the isotopic spin will also be 0. Therefore, we are assigning isotopic spin to the hadrons. We are taking care of the fact that the quantities with the same strangeness, same mass, same spin, we are placing in a doublet, and quantities with the same mass, when we switch off the electromagnetic interaction, same spin, they are produced, they are put in a triplet, and similarly we have quartet, etc. Therefore, we have singlet of particles, we have doublet of particles, we have triplet of particles, and we have quartet of particles. These particles have got the same nature, same mass, same parity, same spin, and therefore they participate in the also in the strong interaction. These are the various examples which I have already discussed. Now, why, as I have told you, this was introduced in particle physics to understand a given process, whether that process takes place via a strong interaction or electromagnetic interaction or weak interaction. Now, I as well as its projection I3, both are conserved in a strong interaction process. I and I3 both are conserved in a strong interaction process, while in electromagnetic interaction, I is not conserved while I3 is conserved. In weak interaction process, neither I nor I3 is conserved. Therefore, in a strong interaction, both I and I3 are conserved. In electromagnetic interaction, I is not conserved, but I3 is conserved, and in weak interaction, none of them are conserved. Therefore, the important point is that if we have been given a reaction, then by applying this isotopic spin, assigning isotopic spin to the particles and looking at the total isotopic in the initial state and the total isotopic spin in the final state, we can say that the process is taking place via strong interaction or electromagnetic interaction or weak interaction. And then let us come to the algebra. This I have already discussed in the case of total angular momentum. Suppose A and B are the particles in the initial state and 1 and 2 are the particles in the final state, then the total isotopic spin will be from IB minus IA to IB plus IA in magnitude, and similarly from I2 minus I1 to I2 plus I1, while the projections are algebraically added. Just for example, if just let me give you an example. Electron proton in the initial state and electron proton in a pi 0 in the final state. Now mind it, we are talking about electron also in this process, and since electrons do not participate in a strong interaction, therefore for sure it can be either electromagnetic interaction process or weak interaction process. Now, the other important point, we cannot assign isotopic spin to the leptons because or the mediating quanta. These are for the hadrons. Therefore, while assigning isotopic spin, we have half for the proton, half for the proton, and 1 for the pion. And now you see what I have told you, 1 minus half to 1 plus half in steps of unity. That means this will be half and 3 half. While on the left hand side, you have half. Therefore, half is here on the right hand side and half is here on the left hand side. Therefore, you are, in this case, conserving isotopic spin, as well as when you take the example of third component of isotopic spin, you have I3 plus half, and this is 0. Therefore, you are conserving I3 as well as I, but since electron is there, which do not participate in a strong interaction process, therefore, this has to be an electromagnetic interaction process. Let us take another example where we have delta plus plus decaying into proton plus pi plus. Now I is 3 by 2. This is half. This is 1. Again, 1 and half can give you half and 3 by 2. Notice that 3 by 2 is here and 3 by 2 is here. Therefore, I is conserved. Then projection, delta plus plus is the highest charge state. Therefore, this is plus 3 by 2. This is plus half for the proton and plus 1 for pi plus. These are algebraically added. Therefore, this will give me just plus 3 by 2 on the right hand side, and we have plus 3 by 2 on the left hand side. Therefore, we are conserving I as well as I3. That is why this will be a strong interaction process. Mind it one thing, that whenever you assign isotopic spin to the hadrons, don't put any sign. When you are assigning the projection of isotopic spin, then only these hadrons will have a plus half or minus half or plus 3 by 2 or minus 3 by 2, etc. Don't give, never assign, like in the angular momentum J, never assign any sign before angular momentum J. J is 1, J is 2, J is 3, J is half. But when you talk about the projection, then only the projection can be plus half or plus 1 or 0 or minus 1, etc. Similarly, I have taken different examples to convince you that how to conserve, see that the process is via a strong interaction or electromagnetic interaction or weak interaction process. Here I have taken the example of pi minus plus p going to pi 0 plus n. As you can see that I is getting conserved as well as I3 is also getting conserved. Therefore, this process will be a strong interaction process. Similarly, let us take another example. Gamma plus p going to p plus pi 0. Photon is not a hadron. Therefore, I am not assigning any isotopic spin to it. Proton has the isotopic spin half, and then on the right hand side we have another proton which have isotopic spin half, and a pi 0 which has isotopic spin 1. And then we are talking about the projections, and we see that photon is there, and photon is the quanta of electromagnetic interaction. Therefore, this process, though it's conserving both I as well as I3, but if leptons are there or if photon is there and you are conserving both, then that will be an electromagnetic interaction process. Similarly, you have electron proton and electron neutron and a pi plus. Here also you will see that both I and I3 are conserved, but that electron is there or muon is there or tauon is there, then that will be an electromagnetic interaction process. Now, if we have electron plus proton in the initial state and electron plus lambda 0 plus k plus in the final state, now you see that lambda is an isosinglet, I is 0. I is 0, we call it as isosinglet. Similarly, isodoublet, isotriplet, isoquadrat. Therefore, I is half a proton. For lambda 0 is 0. For k plus it is half. See, I am not putting any sign before these numbers for I. While I3, I am always putting some sign, either plus half or minus half or plus 3 by 2, minus 3 by 2. And as you can see that both of them are getting conserved. But since this is here, electrons are present, therefore this will be an electromagnetic interaction process. Besides that, there is another important catch. If you notice, lambda and k plus both are strange particles. And what is the strangeness quantum number for lambda plus? Lambda, this is minus 1, and here this is plus 1. Therefore, the total strangeness is conserved, and that means we are talking about associated production of particles. Therefore, we have discussed it already in one of the classes that if you have the projection of strange particles either through strong interaction or through electromagnetic interaction, always they will be in pairs to conserve strangeness quantum number. While if you are producing a strange particle in the weak interaction, then you can have a single strange particle in the weak interaction process. You can only have one strange particle in the final state for any of these processes if you have one strange particle in the initial state. Therefore, this is an important point, that if we are talking about the production of strange particles through strong interaction or electromagnetic interaction processes, always that will be in pairs. Similarly, instead of lambda 0, we can see that whether we can have a sigma 0 or not. E minus plus P going to E minus plus sigma 0 plus K plus. You notice that baryon number is here, lepton number is here, charge is getting conserved. Then you are conserving all the exact conservation laws. Now let us come to the isotopic spin. I is half. For sigma comes in triplet. Therefore, I will be 1 for them. And this is sitting in the middle. Therefore, the third component will be 0, plus 1, 0 and minus 1. Therefore, this will be, I3 will be 0. This is plus half. And then K plus and K0, they are member of a doublet like here. Therefore, this will be half and this is plus half. Notice you are conserving I, you are conserving I3. Therefore, this will be a possible process. And what is the important point? The strangeness quantum number for sigma 0 is minus 1 and for K plus it is plus 1. Therefore, you are conserving total strangeness, and you can see that you are producing two strange particles simultaneously, and therefore this will be another example of associated particle production process. Similarly, take it as a homework whether you can have sigma plus K0 as the particles in the final state or not. You can see that again strangeness is minus 1 here, and K0 is the member of this K plus doublet which has strangeness quantum number plus 1. Therefore, you will see that it's getting conserved. Therefore, the important point is, while classifying them, you will be also able to understand that if leptons are there and you are conserving both I and I3, then that will be an electromagnetic interaction process rather being a strong interaction process. Or if photon is there, then that will be an electromagnetic interaction process, because the photon is the quanta of electromagnetic interaction. Similarly, I have given another example. This is P bar. And you see that proton and neutron were kept in a doublet, because this had charge +1 in units of electronic charge, this had charge 0, while anti-neutron and anti-proton has charge -1 in units of electronic charge, this is 0. Therefore, now anti-neutron is sitting at the top and anti-proton is sitting at the bottom. I3 will be -half for anti-proton and it will be +half for the anti-neutron. Therefore, here I am assigning it. And the other important point that is important to discuss is the following. See here on the right hand side, I is half for one proton, I is half for another proton. Therefore, the total I that I have from here is 0 or 1. While if you take these two, you will have 0 and 1. Then you will combine half with it, and it says that you have to go from 0 minus half to 0 plus half. That means just half you will get from here. But for the other, you will go from 1 minus half to 1 plus half. That will be half as well as 3 by 2. Therefore, when you have taken 3 together, you have the possibilities as what? You have the possibilities as half and 3 by 2. Therefore, when you have taken 3 of them, the possibilities of I that you are getting, they are half and 3 by 2. Then you are adding this half from here. Then again this will go from half minus half to half plus half, as well as it will go from 3 by 2 minus half to 3 by 2 plus half in steps of unity. Therefore, what you notice, the possible values are 0, 1, 2. Therefore, in the final state, you have I as 0, 1, 2. And in the initial state, you have 0, 1. What we require is any one of these numbers should exist on the right hand side to conserve isotopic spin. Therefore, in this process, isotopic spin is being conserved. And then what I have told you, that projections are algebraically added. Therefore, plus half will give me +1, and this will, when sum up, this will give me +1, because this plus half and minus half, that will be equal to 0. Therefore, this is an important point. This is an important catch to understand that how do we take care of different isotopic spin of the particles and then sum them over to get a net I or to get a net I3. To get net I3, we just algebraically sum them, but to get net I, we have to take consider the fact that we have to go from I1 minus I2 to I1 plus I2, and then whatever we are getting, then we have, suppose I'm talking about 1, 2, 3. For example, I1 minus I2 to I1 plus I2. Let us call them by the name I prime, I double prime, in steps of unity I4. And then I have to consider the third. Therefore, this will be I prime minus I3 to I prime plus I3 in steps of unity. I double prime minus I3 to I double prime plus I3, and similarly I4 minus I3 to I4 plus I3. And say I am getting the values by combining these three isotopic spins of the particles to be, say, 1, 2, 3. While on the left hand side we have only 1. So therefore, we will look at this, that one number should be common to conserve isotopic spin. And then we will say that this process is conserving isotopic spin. And then when we will look at the third projection of component of isospin, and that we have to see that is algebraically, we have to add them over to get the results. Therefore, this is another example where you can see that we have a K minus in the initial state and a proton. What I had told you, that if you have, considering a strong interaction, you can have one strange particle in the initial state and one strange particle in the final state to conserve strangeness. You cannot violate strangeness quantum number in the case of strangeness, strong interaction, and therefore what you are noticing, that strangeness for this is -1, strangeness for this guy is -1. Therefore, strangeness in the initial state is the same as the strangeness in the final state. While isotopic spin, we place K0 bar and K minus in a doublet, where this is neutral, therefore it will have maximum projection. This has got a negative charge, therefore this is -12, and here sigma 0 in a triplet, I3 is 0. Therefore, this is how you can see that you are conserving both I as well as I3. Therefore, this is an example of a strong interaction process. If I take, for example, nu mu bar plus P going to mu plus lambda. Now, the important point is neutrinos are the particle which participate only in weak interaction process. Therefore, this cannot happen in strong and electromagnetic processes. Therefore, if neutrino is there and you are conserving lepton number, baryon number, charge, and etc., then the process has to be a weak interaction process. For example, if I say that I is half and here it is 0, I3 is plus half and 0, you are saying that neither you are conserving I nor you are conserving I3. This will be a weak interaction process. Similarly, you can consider, instead of lambda, you can have a sigma 0, where you can have, this is 1 and this is 0. Therefore, and you see, I am not assigning any isotopic spin to the leptons. I am assigning isotopic spin quantum number and the projection of isotopic spin to the hadrons. And therefore, sigma 0 isotopic spin is 1, whose projection is 0. Therefore, here also, neither you are conserving isotopic spin nor I3. Therefore, this is an example of weak interaction process. Therefore, you have the strong interaction process, you have the weak interaction process, and you have the electromagnetic interaction process. I have taken another example of sigma plus. This is another, for example, if I am talking about the decay of sigma plus to pi plus and n. As you may recall, when I was introducing strange particles, I had told you that strange particles in strong interactions are produced in pairs. In electromagnetic interactions also they are produced in pairs. While in weak interaction you can have a single strange particle, as we have seen in the previous example when we had only a lambda in the final state. Then when these strange particles decay, they decay via weak interaction. They have a very long lifetime of the order of nanoseconds, picosecond, etc. Therefore, when I am talking about decay of lambda, decay of sigma, decay of omega, decay of any strange particle, whether a K plus or K minus, it will take place via weak interaction. And you can see that when we are talking about weak interaction, then neither I nor I3 will be conserved. And as you can notice, here we are taking the example of sigma plus decaying into pi plus n. Sigma plus is a member of isotriplet. Pi plus is also a member of isotriplet, while neutron is a member of isodoublet. We are assigning I equal to 1 for sigma plus, 1 for pi plus, half for neutron, and then maximum charge will get the highest projection, plus 1 for sigma plus, plus 1 for pi plus, and minus half for neutron. As you can see that from here, you will get the value as half and 3 half. Therefore, you don't have any number half and 3 half on the left hand side. Therefore, this is getting violated. And then plus 1 and minus half, they are algebraically added. Therefore, this will give me plus half only. And you have here plus 1. Therefore, you are neither conserving I nor you are conserving I3. Therefore, this is another example of weak interaction process. Similarly, you can have sigma 0 and lambda 0 plus gamma. Here we also introduce a particle, a quantum number that is known by the name hypercharge. Hypercharge consists of baryon number plus the strangeness quantum number. Again, this hypercharge is for the hadrons, and it consists of baryon number plus the strangeness quantum number. The significance of this we will discuss later in the class. And for example, if I am talking about proton, then baryon number is plus 1, strangeness is 0, hypercharge is plus 1. For pi 0 are mesons, therefore baryon number is 0. They are not a strange particle, strangeness is 0, therefore Y is 0. For K minus, baryon number, K minus is a meson, baryon number is 0, strangeness is minus 1, therefore hypercharge is minus 1. And similarly, you can talk about the other particles, like I am talking about, say, lambda 0. Lambda 0 is a baryon, therefore B is plus 1, strangeness is minus 1, therefore hypercharge is 0. If I am talking about, say, sigma plus, then baryon number is plus 1, strangeness is minus 1, then hypercharge is 0. If I am talking about K0, then baryon number is 0, strangeness is plus 1, therefore the hypercharge is plus 1. Therefore, this is how, if I am talking about delta plus plus, it is a baryon, its strangeness is 0, its hypercharge will be 1. Therefore, to the hadrons, we also assign a quantum number that is known by the name hypercharge, and basic level it is equal to baryon number plus strangeness quantum number. But when we will consider the charm and bottom baryons or mesons also, this will get further added, that we will discuss. Now, what has been found by Gell-Mann and Nishijima, that the charge of the hadron is equal to the third component of isospin plus y by 2. This y is b plus s. Therefore, if I am talking about, say, a proton is a member of isodoublet with the projection plus half. Its baryon number is plus 1. Its strangeness is 0. Therefore, from here you can see that plus half 1 by 2, that is plus 1. Therefore, similarly, if you take lambda 0, baryon number is plus 1, strangeness is minus 1. This is an isosinglet. Therefore, the net charge would be 0. If you talk about other particles, similarly, you can just put the values of these quantum numbers and you will get the charge of the particle. This is known as Gell-Mann and Nishijima relation. Now, further, if we move ahead, then when we will talk about charmness, bottomness, and topness quantum numbers, then this is given by y is equal to b plus s plus c plus b plus t. This is charmness. For example, if I am talking about a particle which is made up of C d bar quarks, then charmness quantum number is plus 1. While if you will look at my previous lectures, for bottomness, we assign bottom quantum number to be minus 1, topness quantum number to be plus 1. Therefore, if we have a top quark, the topness quantum number will be plus 1. Anti-top quark, topness quantum number will be minus 1. For bottom quark, the bottom quantum number will be -1, or anti-bottom quark, the bottom quantum number will be +1. While therefore we have straightness quantum number, we have charmness quantum number, we have bottomness quantum number, and we have topness quantum number. Charmness quantum number is +1, straightness quantum number is -1, bottomness quantum number is -1, while topness quantum number is +1. Therefore, this is how we assign the hypercharge to the particles which have straightness, which are even charm particles, or which can be carry a bottom quark or a top quark, like that. Therefore, the study of mesons and baryons revealed patterns that could not be explained solely by the known particles, protons, neutrons, and pions. That is what we have seen in the lectures. We saw that there are many more particles. These inconsistencies led to the proposal of quarks as subatomic constituents, each carrying fractional electric charge. Therefore, let us stop here, and in our next lecture, we shall start the discussion on the fact that why this quark model came, what was the physics behind it, why we were sure that these hadrons are not the fundamental objects, they are made up of quarks, three quarks, or quark anti-quark pair. Therefore, we shall start from this point to convince you that quarks should exist, and then later in the experiments like that of Rutherford alpha particle experiments, we have found that really quarks are there. Let us stop here. Thank you very much.